changing Gil, you should know Gil. What is not changing in Gil, what is long-lived, and that is this smile. A smile of joy and curiosity. That characterizes Gil. But behind this smile, there's a razor-sharp analytical mind that transcends a huge spectrum of capabilities from theory and methodology all the way to real, meaningful applications in biomedicine. These are not taken from the internet. These are pictures that we actually took. This was taken by my wife. This was taken when Gil was visiting in Berkeley. So Gil, it's been a pleasure to know you, and I'm going to talk for a very short time about the interaction that we had that led to something, because of you, that actually has some applications in biomedicine, something I'd never intended. So, Gil, when you came to Berkeley, you were already past the days of solid-state NMR, at least in my laboratory. It was still doing some. But it had developed into a pretty robust tool, and my interest had shifted towards the notions of new polarization methods, new detection methods, using non-inductive detection, and perhaps reducing everything onto a portable, microfluidic scale of potential use. I hope this microphone will grow and flourish and give rise to many more little microphones. I'm sorry to be such trouble, but one of the things we want to do is to marry the advantages of optics in sensitivity and the fidelity of NMR and MRI. And we do this both by polarizing and by detecting. And noble gas, chosen specifically because of Gil's intersection with that, polarized with a laser. Photons are amongst the few particles that are easy to polarize to 100%. They're spin-1 bosons. They can be polarized to 100%, and that polarization can be transferred to the nuclear spins with a huge enhancement. And Gil, when you came, we were already doing experiments like this, for which, as you know, I was literally giving my blood. And here's the kind of thing that Charlie Springer talked about, the water going in and out of the astrocyte. Here's Xenon, an anesthetic, with two distinct chemical shifts reflecting the physiochemical environment. Here's another example about that time, Gil. You know, that we took Xenon, hyperpolarized with a laser, and put it into a zeolite extended network of cavities. These are about 14 angstroms in diameter. The Xenon atom is about 5 angstroms. And look, you can see distinct quantized signals with large chemical shifts over a range of 100 parts per million for these different occupancies. 1, 2, 3, 4, 5. Cynthia Jemison went up to 7 with this. You can see that it's non-statistical, that it's not random. There's actually an interaction between the cavities with different numbers of xenons. And furthermore, you can do two-dimensional dynamics of exchange. And it's interesting because the physics there is not trivial. You have to work out the occupancies, and you have to ask, what is the probability that an atom will jump to an adjacent atom? And you find it's different. If it's empty, it's more rapid. If it's got a few xenons there already, it's slower. You can work out the theory and capitalize on the sensitivity of xenon to its environment. Here's an example that was prevalent, I think, just before you came, Gil. This is work done with David Wemmer, showing maltose binding protein. We have many examples of this. But this shows that xenon, in the environment of this protein, which changes conformation when it binds the maltose, it's like a Pac-Man. It closes down, and the xenon detects that. So already here, I had the notion that xenon could be used as a sensor, a detector of physical environment, and therefore sense events such as conformational change, and perhaps biochemical binding, both in vitro and in vivo. So as an assay, as a detector, and perhaps as a molecular sensor in vitro and in vivo. The trouble is that this is not specific. This is a case where you only have maltose and the MBP protein in solution. If you have a mixture of things, as you do in complex tissue or organisms, or even in blood samples, then you have an averaging of the environments, and you can't be specific about this environment. So here's the time. I'm going to skip over these. I'll show these tonight. I'm going to test Gil on the identity of every one of you. You notice that my group was shrinking while Gil was there. I have to talk to Gil about that. And of course there was a lot of food and other things. I'll talk about that. This is a rare picture that I found, which I'd like to rejoice in. So when Gil came, one of the things we had in mind was to use Xenon not just as a probe, as a detector, but as a source of polarization. Not in solids, but in liquids. Imagine bubbling Xenon in, laser polarized, and polarizing a solution. And here, in fact, is a solvent, benzene. The protons of benzene are being polarized positively with positively polarized xenon, and negatively with negative polarized xenon, in solution. This is an example of a solution state dynamic Overhauser effect with no pumping needed whatsoever, simply using the natural polarization affected by the laser. A lot of people didn't believe this. They thought that these were spurious signals. And Gil, you remember the interaction with someone whose name I won't mention, but whose initials are Bob Bryant. And I'll show the exchange. I'm going to show it now, but I'll show it tonight at the banquet, which took place in... here Gil became a newspaper celebrity, as you can see here. And again, I'll say something about that later. So here's the paper that came out in Science, Enhancement of Solution NMR and MRI. I got a phone call from said colleague who said, we don't believe these results, they're spurious. They went over the experiments, and their results were published here, but then subsequently they had planned to publish them also in the open literature. And they did this without calling me up and at least chatting about the possibility that maybe there's something wrong with their failure. So I'll talk about that a bit this evening. Gil and I differed here. I wanted to respond. And he said, you respond. I wanted all the authors to sign off on it. The way they did here, you can see the signatures of the disbelievers. So I'm going to be Gil, myself, and other people, and he said, no, I'm going to do that. My style, which is that you go very reticent, very quiet. He said, you do it by yourself. So I'll show you that. Again, I'll show you that later. We did discuss the possibility that our results maybe are wrong for a microsecond or two, and that we might publish it in this journal over here, but instead I did publish a rebuttal because we had got other results in the meantime which were quite dramatic for things like toluene, paranitrotoluene, mixed with benzene, and these results were rather convincing even to the disbelievers. So here is the response, and Barry Shapiro with his unflagging cynical humor entitled Microfusion Failed Failure. This is our attempt to replicate the failure of the University of Virginia group. I'll talk about that this evening. The next thing we wondered was, can you be specific? Instead of solution, can you polarize parts of a molecule in a solution to which xenon will naturally have an affinity? The hydrophobic regions. Cyclodextrin, used to deliver drugs, has a hydrophobic interior, and here's the proton NMR spectrum of cyclodextrin, alpha cyclodextrin, and these peaks are all assigned. Some are on the outside of the ring, some are on the inside of the ring. And when you introduce laser polarized xenon, up or down, you get a specific enhancement of the proton resonances assigned to the inside where the xenon is associated. So this looks like a way to transfer to molecular positions in hydrophobic regions of a molecule. And in proteins, that's a very useful tool. We haven't pursued this, but Hervé Deveau and co-workers in Paris have done beautiful work on probing the hydrophobic regions of proteins by seeing which resonances light up. And you can see if it's unpolarized, you get no excess polarization. So this was published on the cover of Angewandte Chemie called Lighting Up NMR of Molecules. And Gil, I think, was a participant in many of the experiments involving blood, in many respects, and involving the transfer of polarization. And it then occurred to me, gee, if we can do this, maybe we can make the xenon detection of physiochemical environment specific. We can take xenon, which is non-reactive, it's noble, has a huge chemical shift range over physiochemical environment, and functionalize it to make it chemically active without any covalent bonding. And to do this, the idea was to put it inside a tryptophan, into which it fits very nicely, and exchanges in and out conveniently, have a ligand for a target, or have a protein or antibody for a target. Here's the synthesized molecule, a 12-step synthesis by Peter Schultz, currently at Scripps. I'm currently on sabbatical at Scripps for the year, and we're carrying out a lot of work now on very rapid assays using NMR with these biosensors. And you can see here the type of result that we got. You see here the signal of the Xenon NMR itself. It's a doublet because of chiral recognition, something that Aaron Levenstein, who's sitting here, the world expert at, has shown that already, the sensitivity in crystals of Xenon to orientation and to chirality. But you can titrate this, and you can see that it's detecting the target, in this case, streptavidin, and chiral recognition is increasing. So this looks like a viable biosensor. And in fact, recently, very recently, we published results in enhancing the sensitivity to the extent that it's currently, this is 700 femtomolar in 2010 in JAX, but now we're getting into the range of femtomolar, tens of femtomolar, by taking biologically compatible viral capsids. And Matt Francis has decorated the inside of these many copies of the sensor so that there's a strong delivery and it still picks up the signal. We can make a temperature sensor. The idea is that, again, temperature affects the sensor chemical shift, and you can make this a molecular sensor. So if you target something in vitro or in vivo, you can then look at that position molecularly targeted at a local molecular temperature environment. And now you want to find ligands for analytes, so that you can use a range of biosensors to look at complex fluids. Blood is an example, a single platform for analyzing blood. Fluorescence, very tough to screen. Can't look inside opaque, messy fluids. Biofuels, and I should add even the complex fluid wine, and try to correlate properties of the biosensor arrays with functional properties of the fluids. In the case of blood, disease and therapy. In the case of biofuel, its function of the biofuel. In the case of wine, taste, price, and what's called the single functional parameter that determines price these days, the Parker rating. And that's so that we can get bottles of wine from the big producers of wine and take little samples, analyze them, and the rest is used for other purposes. So how do you do that? That's Matt Francis. We're doing very big library screens of ligands for a bunch of analytes, using peptides, peptoids, and aptamers. The advantage of NMR is that, unlike fluorescence, you don't have to label fluorescently. So imagine you can do large-scale screening by looking at the NMR without having to do any kind of labeling, no washout, and have the NMR itself be the screen for the target, and develop in this way a range of biosensors, and that's something that we're doing. The first one was done with fluorescence, and to compare it with the NMR, once that works, we know that the NMR can be used and no need for fluorescent labeling. So we pick beads out that have the positive response of the NMR, and those beads are then further amplified in the library, and that's the kind of thing that I went to Scripps for, with Richard Lerner and Peter Schultz. We're doing some work on this very rapid screening. So the idea is to put this on a microfluidic platform. I'm going to skip through this because of a lack of time. This shows that we can do microfluidics with very high sensitivity because we have these very, very sensitive laser detectors. We can also work without a magnet and do the type of spectroscopy that my colleague and good friend Bernard Blooming showed you. We have a collaboration doing zero field and very low field J spectroscopy as an analytical tool for analyzing molecules without the need for any magnet for either polarization or for detection. This is an example of a J spectrum of, in this case, benzaldehyde, and the resolution is down in the range of 0.01 hertz. So the kind of spectrum that Bernard showed at the Earth's field, we can do this down at zero field or mildly perturbed by Zeeman couplings to give you an additional and a fingerprint. We use other techniques as well. Again, in the interest of time, we're going to stop well in the green region here and conform to Douglas' request to finish up. As I said, I'll show more pictures later. I'd like to say thanks to my group, some collaborators here you will see. You can see John Clark, Matt Francis, who does the library screening, Francis Speck, making chromatographic monoliths, which we want to study by microfluidic NMR, David Wemmer by physical NMR, yes, Bernard Blumig. Thomas Schenkel is making diamonds embedded with defects that can be used to fluorescently detect magnetic resonance. So they're NV centers, and we have a big program in that, a big program in nano diamonds, little diamonds, because those can be used in a modality of NMR with no magnet and no magnet for detection, using a laser on the diamond to scan across samples. These can be cell tissues or small nanomaterials, and give local magnetic resonance spectra with spatial resolution down in the range of nanometers. So that's a rather substantial program in my lab, and Thomas Schenkel is one of the participants. Mickey Butker, laser detection together with John Kitching at NIST in Boulder. And finally, I'll show this again tonight. Ruthie's not here, but I think she'll be at the banquet tonight. I hope she will. This is a picture of Gil during his formative years when he spent time with Monet, which you can see over here. And I want to say to Gil and to Ruthie, to many more years of health, joy, happiness, and Ad Me'er Etzrim, 120. Thank you.
Other questions or comments? No. I'll press the note later. If there are no questions, you still have a chance later in the evening to ask Alex. But let's thank him again before asking you to come. Gil, the stage is yours.